We have a trough that's 50 feet long and has semicircular ends with the flat side facing up. So here we have a picture of our trough. The semicircles have a radius of 10 feet. Okay, so the trough is 50 feet long and the radius here is 10 feet. If the tank is filled to a depth of 6 feet, find the work done pumping the water over the rim. So this is also 10, but the tank is only filled to a depth of 6 feet here. Okay, so as we want to pump this out, when we think of computing work, we know that the work is we need to take the force times the displacement, and the force is mass times acceleration. The mass, we're going to represent that as volume times density. So we're going to use rho for our density, and we need the volume of a slice. So if we took a horizontal slice here, what would it look like? It would actually look like a rectangle. It would look like what the top of the tank looks like. So we've got a slice here turned so we can see our rectangle, and we know its length is 50. Now we need to figure out its width, and that's going to be based on how high you are. So let's look at the semicircle. I have an enlarged one over here so we can look at it a little bit better. And let's go ahead and put a coordinate axis on it. And I'm going to do this one a little different because it's going to make it the easiest way to work with it. I'm going to put the origin at the top in the center of that semicircle, and I'm going to let the positive y be measured from the origin and go down. This is not uncommon in physics. If you had a spring mass system and you have it hanging vertically, a stretched spring, which is in the downward direction, is positive, and compressed, the upward direction is negative. So we'll do something similar here because this will make this easier to work with. All right, so if I take a representative slice somewhere, goes across like that, I'm interested in that end I just showed across would be this end of this rectangle. So it would be our width here. And so what would that be in my coordinate system? Well, I can see that this would be x, and there'd be two of them to get that whole width. And then measuring from the origin down, this part would be y. So my little width is going to be 2x, but to put it in my integral, I need it in terms of y because my little thickness is in the y direction, a little dy. So do we have a connection between x and y? And we do. We can form a right triangle by making a hypotenuse over here. And we know that the length of that hypotenuse is 10 because that went from the center of the semicircle out to the semicircle, and so it's a radius, and so it's 10. So our connection there is going to be x squared plus y squared equals 10 squared, so we can easily solve that for x. It's going to be the square root of 100 minus y squared. Now what we want for our little width is 2x, so we could just multiply both sides by 2, and this is what I'll use for my little width. So I'm wanting to compute the volume of that little slice, and so it's going to be length times width times thickness, and so I've got 50 times 2 square root of 100 minus y squared, and then my little thickness is dy. This was mass, which was density times volume, and so I need my acceleration, which is g. And so now I have my force and I need my displacement or distance. So if I look here and see what is the distance to get to the top of the tank, that is just going to be y, because we measured from 0 and then we go down for y. So wherever our representative slice is, that is y away from the top of the tank there. Let's get our limits of integration then. We know down at the bottom here then, because the radius was 10, is going to be 10, and up at the depth of that, which was 6, the y is going to be 4. So we're going to go from 4 to 10. And let's go ahead now and see what we can do to work that integral. I'm going to move the constants out in front. So I have work equals, we've got 50 times 2, so I've got 100 rho and g, and then I'm going to integrate from 4 to 10, and I'll put my y out in front of the radical so I can see what I might want to do to work this integral. Now, as I'm looking at that integral, I can see that it would work nicely to have for a u substitution. U would be what's under the radical, 100 minus y squared. So du would be negative 2y dy. And actually, I could steal a 2 from the 100 and make it 50 and put it a negative 2 if I make that also negative. Okay, so I have my du. It is negative 2y dy, and this part under the radical is my u. So let me rewrite that integral now in terms of u. So that's going to be negative 50 rho g. I'm going to need to change my limits of integration to get them in terms of u. I'm going to do that in just a minute. So I've got my du there, and then I have u to the 1/2. I'm actually going to slide that over so I'll have room on the slide. So u to the 1/2 du. Limits of integration, 4. We need to plug 4 into our equation that tells us what u equals. 100 minus 4 squared. So 100 minus 16 is 84. And then let's put 10 in. 10 squared, 100 minus 100 is 0. All right, let's go ahead and work the integral, and then we can evaluate it. So I'm going to have negative 50. I'm going to go ahead and put in my rho g for water in our units. It would be 62.4 pounds per cubic foot. So I'm going to go ahead and replace that. And then if I had one higher power, that would be to the 3/2, and I need the reciprocal of the power out in front, and evaluate that from 84 to 0. All right, so that's going to be negative 50 times 62.4 times 2/3 times upper limit is 0, and then minus, we're going to have 84 to the 3/2, and so we want to round that to the nearest foot-pound. So let's go ahead and put that in the calculator, and it looks like we get, trying to figure out where to put it. I'm going to go ahead and put it up here in my representative slice. 1,601,335 to the nearest foot-pounds of work.